Okay, so it's page 19 in your package. Package.
I see you're repping the Jays today.
I am,
Very
yes.
nice, very nice.
Another 6 weeks or so, catchers and pitchers will be reporting.
Always excited for baseball.
Yeah. All right, so we're going to look at evaluating some more limits today. And then you guys have a quiz tomorrow on evaluating limits. So it's just going to be based on basically these last two lessons. Okay? So we have seen that when you're evaluating limits, you're trying to find the value that the function is approaching as x or whatever the variable is gets closer to a specific number, a specific value. In this case, what is x cubed minus 64 over x squared minus 16? What is the value that approaching as x gets closer and closer to a value of positive 4? We saw that in many, but not all cases, the value that the limit is approaching is a non-permissive value, and that's the situation here. If you let x equal 4, the denominator will be 16, take away 16, which is 0, and you can't have that. So we need to do something to evaluate this limit. But it's always a good idea to just quickly check to make sure that the value that x is approaching is a non-permissive value, because if it's not, you can just substitute it in and get your answer. But that's not the situation here. So we need to do something to that function in order to be able to sub in a value of x equals 4 in the denominator. And that something, once again, is factoring. So the numerator is a difference of cubes, because you can take the cube root of both x cubed and 64, and there's a minus sign in between. The cube root of x cubed is x, the cube root of 64 is 4. That gives you the terms of the binomial. The terms of the trinomial are found by squaring the x, multiplying the 4 and the x together, and squaring the 4. And then you need to remember the sign pattern for difference of cubes is minus, plus, plus. All over x squared minus 16, which is a difference of squares, x plus 4, x minus 4. And I forgot to put the limit part in there, so I will make sure I add that in my next step. So what happens then is that the x minus 4's cancel, and we've now gotten rid of the part of the denominator that makes 4 a non-permissive. Now the non-permissive value is negative 4, but that's fine because we're not asked to find the limit as x approaches positive or negative 4. We're asked to find it as it approaches negative 4. So this will be the limit as x approaches 4 of x squared plus 4x plus 16 over our x plus 4. And now we can evaluate that by letting x equal 4. So we'll have 4 squared plus 4 times 4 plus another 16 over 8. So that'll be 48 over 8, which is 6. So that's the value of that limit. In this case, if you were to graph that rational function, you would have both a point of discontinuity and a vertical asymptote, because you still have a denominator of x plus 4. That makes negative 4 non-permissive, but you get a vertical asymptote there. At positive 4, because the x minus 4 is canceled, that's where you'd have a point of discontinuity. The point 4 comma 6 would be a point of discontinuity, a hole or a break in the graph. Okay? Looking at number 2, you want to find the limit of that function as x approaches a value of pi. Well, pi is a non-permissive value because you have a denominator of x minus pi. So we need to do something to this function to get rid of the x minus pi on the bottom. And once again, that something would be factoring. The top is difference of squares. It'll be x plus pi and x minus pi. And then the x minus pi's will cancel. And so you're left with the limit as x approaches pi of just x plus pi, so you'll have pi plus pi, or 2 pi. So that function approaches a value of 2 pi, approximately 6.28, as x gets closer and closer to positive pi. Looking at number 3, the limit as x approaches root 2, which is a non-permissive value of x cubed, take away 2 root 2 over x minus root 2. So we can factor the top as a difference of cubes, and here's why. I've got the limit as x approaches root 2, and again I said the top, the numerator, can be factored as a difference of cubes, because I could rewrite that to x cubed take away the root of 2 all cubed. That is equivalent to the original expression. You see, if you multiply root 2 by itself 3 times, and I'll just do it above just to show you. So that means root 2 times root 2 times root 2. Well, the first two root 2's multiplied together would give you root 4 or 2. So you're left with 2 root 2, which is what the second term is originally on top. So that just shows you that you can rewrite 2 root 2 as the square root of 2 cubed, which again makes it a difference of cubes. So I've got the limit as x approaches root 2. Again, if I'm going to factor the top as a difference of cubes, the cube root of x cubed is x. The cube root of root 2, all cubed, is root 2. So that gives you the terms of the binomial. To get the terms of the trinomial, we square the x. We multiply the two terms together, so I'll write that as x root 2. And then we square the last term, which is 2. Again, this is a difference of cubes, and the sign pattern is minus, plus, plus. And the denominator I leave as x minus root 2 because I'm going to cancel it with that same factor above. So now we can evaluate this. When you square the root 2, that's just going to give you 2. Plus then you're going to have another root 2 times root 2. Another 2 plus another 2, which gives us an answer of 6. So as x gets closer and closer to root 2, the value of that function will approach a value of 6. But that is a non-permissive value, because at x equals root 2, there would be a hole in the graph. There would be a point of discontinuity. And that point of discontinuity would be at the point root 2 comma 6. This graph would not have a vertical asymptote, because there are no factors left on the bottom. Okay, in this case 4 is a non-permissive value, so we need to do something. And that something in this case would be factoring the top as difference of squares. Right? Even though the x isn't squared, you can still take the square root of x by writing it as the root of x, which is what we need, because look at the denominator. It's the root of x take away 2. So this will be the limit as x approaches 4. And if I factor the top as difference of squares, we take the square root of the first term, which will be root x. The square root of 4 is 2. One's a plus, one's a minus. So the root x's take away 2 cancel, and we can now evaluate that by letting x equal 4. So we'll have the root of 4 plus 2. The root of 4 is 2 plus another 2 gives us 4. And so there's your answer. So again, in this case, you would have a point of discontinuity at the point 4 comma 4. if you were to draw that graph. Number 5, I'd probably start there, well, first by saying that 3 is a non-permissive value. So to evaluate this limit, what I would first do is I would multiply all of the terms on top and bottom by 3x. Because that is the common denominator for the denominators and the numerator. So when you multiply that first term, the 1 over x by the 3x, the x's cancel. The second term on top, the 3's will cancel. And this just makes it a little easier to work with. So I'm going to have the limit as x approaches 3. And I'm left with 3 take away x. And on the bottom, I'm not going to multiply those out. I need to get rid of the x minus 3, that factor of x minus 3. So I'm not going to multiply the bottom out. I'm going to leave it in factored form. So that's where I am right now. Now, 3 minus x is not the same as x minus 3. They are in fact opposites, because on the top, the 3 is positive. On the bottom, it's negative. On top, the x is negative. On the bottom, it's positive. They are opposites. I can make them the same, though, by taking out a common factor of negative 1 out of either the top or the bottom. If I take out a common factor of negative 1 from the top, I'll get negative 3 plus x, or x minus 3. And so now the x minus 3's cancel. And now we can evaluate this limit as x approaches 3 by letting x equal 3 in the simplified expression. It would be negative 1 over 9. So this would be one that would be difficult to do it by a table of values, using numbers closer and closer to 3 for x, or even a graph, because you'd have to guess what the y value is as x gets closer and closer to 3. And in this case, that y value is negative 0.1 repeating. Number 6. This is a difference of cubes. And 0 is a non-permissive value for d. So we're going to have the limit as d approaches 0. So the cube root of 3 plus d all cubed is 3 plus d. The cube root of 27 is 3. Whoops. This should have been 3 plus d all squared. So to get the terms of the trinomial, you're going to square the first term. You're going to multiply the two terms together. And you're going to square the last term. Squaring the 3 gives us 9. And the sign pattern for difference of cubes, again, is minus, plus, plus. All over d. You with us, J-Head? So on top, that first factor, the 3's will cancel. 3 take away 3 is 0, so you're just left with the factor of d on top, which will now cancel with the d on the bottom. So that'll give us the limit as d approaches 0. And you don't actually have to simplify what's left on top. We can just leave it as is. Because all we need to do now is just let d equal 0 to get our answer. So when d equals 0, you're going to have 3 plus 0, which is 3 squared is 9, plus, when d equals 0, you're going to have 3 plus 0 inside the brackets, which is 3 times the other 3 is 9, plus another 9. Our answer is 27. And again, you would have a point of discontinuity at the point 0, 27 for this graph. Okay? Number 7, p is a or 0 is a non-permissive value for p. But I would first start by getting rid of the denominator in the numerator by multiplying all the terms by the common denominator from the numerator, which would just be p plus 1. And the whole point of doing is that those p plus 1s cancel there. And we are left with the limit as p approaches 0. So you're going to have 1 on top, take away, because now it's negative 1 times the p plus 1. So it'll be negative p minus 1. And again, I'm not going to multiply out the bottom. I want to get rid of that factor of p on the bottom, which I can do because when I simplify the top, I'm going to have the limit as p approaches 0. 1 minus 1 cancels, so you're left with negative p over p bracket p plus 1. And now you can divide top and bottom by p. And we've gotten rid of that factor of p on the bottom that was causing the issue. So we're left with the limit as p approaches 0 of negative 1 over p plus 1. And now when p equals 0, you'll have negative 1 over 1 or negative 1. Okay? Question 8. 0 is a non-permissive value. So we need to do something to get rid of that factor of y on the bottom. And that something in this case would be multiply top and bottom by the conjugate. You can't really factor the numerator as difference of squares. I mean, you could, but then that first term would be the square root of y plus 16. It's not going to help us. We have to get a factor of just y on top so that we can cancel with the y on the bottom. So that's something that I would do, would again be multiply top and bottom by the conjugate of the top, which would be the root of y plus 16 plus 4, both top and bottom. So on top, when you multiply the root of y plus 16 by itself, you're just going to get y plus 16. When you multiply conjugates, the outer and inner products always cancel. That's why we're doing it. You'll get 4 root y plus 16 minus 4 root y plus 16. They cancel. So now I just multiply the two last terms together. Negative 4 times positive 4 is minus 16. And so you're going to be left with y on top, which will cancel with the factor of y on the bottom, which is what we needed. And again, I wouldn't multiply out these brackets on the bottom because that defeats the purpose. We need to get y by itself. So the 16 take away 16 is 0. We're left with the factor of y on top. We can divide top and bottom by y. And we've gotten rid of that non-permissive value. So we are left with the limit as y approaches 0 of 1 over the root of y plus 16 plus 4. And when y equals 0, 0 plus 16 is 16. The square root of that is 4. On the bottom, you're going to have 1 over 4 plus 4, or 1/8. And once again, if you were to graph this, there would be a point of discontinuity at the point 0, 8. It's another one that would be very difficult to get that answer by using a table of values or even a graph, because the answer is a decimal, 0.125. Number 9 would be done the same way, right? We need to do something so that we can get a factor of x on top to cancel with the x on the bottom. can't really consider the numerator to be difference of squares because that first term would be the root of x plus 1, which isn't going to help us. So once again, I would multiply top and bottom by the conjugate of the top, which would be the root of x plus 1 plus 1. So on top, when you FOIL this out, the root of x plus 1 times the root of x plus 1 is x plus 1. The outer and inner products would cancel. So you're just multiplying the last terms together. Negative 1 times a positive 1 is a negative 1. Those 1's will cancel, and you're just left with the factor of x on top, which will cancel with the x on the bottom. So we are left with the limit as x approaches 0 of 1 over the root of x plus 1 plus 1, which we can now evaluate. When x does equal 0 on the bottom, you're going to have the root of 0 plus 1, which is the root of 1 or 1 plus another 1 gives us 2. And so there's the value of that limit. And remember, on Friday we saw that sometimes you cannot do something to the function to eliminate the non-permissive value on the bottom. And so in those cases, we need to do it graphically. Right? So you've got the limit as x approaches 0, 1 over x. 0 is a non-permissive value. So let's look at the graph of 1 over x. So this is a rational function. So remember, these rational functions normally have two different parts that are in opposite quadrants, usually. Okay. Also, we have asymptotes here. 0 is a non-permissive value at x equals 0. So that means that the y-axis is a vertical asymptote. And in this case, the x-axis would be a horizontal asymptote. And the reason we know that is because y can never equal 0. If you have y equals 1 over x, there's no number you can put in for x to make y equal 0. Because 1 over something is always something. It can be positive, it can be negative, but it'll never be 0. The only way a rational function equals 0 is if the numerator equals 0. Because then you'll have 0 over something. And the numerator in this case is a constant. So that is how we know that the x-axis is also an asymptote. Also, if we look at the function and we realize that when x is positive, 1 over a positive value is a positive value. Right? When x is 1, 1 over 1 is 1. So that's that point right there. When x is when x is 2, 1 over 2 is a half. When x is a half, 1 divided by a half is 2. So this just shows us that the one arm of this graph is in the top right quadrant. And then it approaches that asymptote. And when x is negative, y will also be negative. When x is negative 1, 1 over negative 1 is negative 1. When x is negative 2, you're going to have 1 over negative 2, or negative a half. When x is negative a half, you're going to have 1 over negative a half, which is negative 2. So again, this just shows that the other arm of this graph is in the lower left quadrant. So that's what that graph looks like. And we saw an example like this yesterday. On the right side of 0, as you get closer and closer to 0 from the right, the graph is approaching positive infinity. On the left side of 0, as you get closer and closer to 0 from the left, the graph is going downwards forever. It's approaching negative infinity. This is an example where the limit does not exist. Because the graph is approaching different values on either side of 0, which is what x is approaching. So the limit does not exist. Okay? You don't have this one? Okay. It's another one that you would have to do by graphing. But the difference here is that because the denominator is squared, the denominator is always going to be positive. No matter what number you put in for x, like let x equal -5, inside the bracket -5 plus 2 is -3, but then when you square it, you get +9. Okay? So in this case here, the denominator is always going to be positive. And because of that, the graph will always have positive values for y, right? You are going to have a non-permissive value here of -2, because when x is -2, -2 plus 2 is 0, squared is still 0. And so because of that, you're going to have a vertical asymptote at -2. Once again, the x-axis will be a horizontal asymptote because y can never equal 0. The only way a rational function equals 0 is if the top equals 0, and in this case the top is a constant, so it can never equal 0. We already stated that the denominator is always going to be positive, so this graph will always have a positive value of y, because 1 over a positive number is always a positive number. When you let x equal 0, 0 plus 2 is 2, squared is 4, but 1 over 4 is 1/4. So that's really, really close to the horizontal asymptote. When x is -1, -1 plus 2 is 1, squared is 1, you're going to get 1 over 1. So that's that point there. So this just again shows us that the one arm of the graph would look something like that. And now if I choose some numbers for x to the left of -2, let's say -3, on the bottom when x is -3, -3 plus 2 is -1, but when you square it, it becomes +1. And 1 over 1 is 1. So -3, 1 is a point on the graph. If I let x equal -4, -4 plus 2 is -2, squared is still 4, you're going to get 1/4. Again, very close to the horizontal asymptote. So this shows that the other arm of the graph would look something like that. And in this case, on either side of -2, the graph is approaching the same value. It's approaching a value of +infinity. That's the answer to this limit. As x gets closer and closer to -2 on either side of the asymptote, that graph just keeps going higher and higher. It approaches a value of +infinity. And so that's the value of that limit. Okay? So again, sometimes you need to look at the graph in order to determine what the limit is, because there's nothing you can do to the equation to get rid of the non-permissive value. All right. Page 19 to 20. Questions 4, E through H. Questions 5, A through E. And 6, A through G. So again, for question 5, that's A through E, not C. Same thing with number 4. It's E through H, not C. And you're going to hand this one in for marks. So do it on a separate piece of paper. Make sure your name's on it. And then you'll put it on the corner of my filing cabinet there. And so this will go into Power School for marks. And then again, you have your quiz tomorrow. Okay?